Hi students, welcome back to the session on free vibration. So in this the video, we're going to see the problems on damped systems. So let us consider a problem. Determine the critical damping coefficient, damping factor, the natural frequency of a damping vibration, the logarithm decrement, ratio of two consecutive amplitudes of a vibrating system, which consists of a mass of 25 kg, a spring of stiffness 15 kilonewton, and a damper. The damping provided is only 15% of the critical damping. So this is the question they given. So from this question, what are the given data I can take? One is the mass, so that is 25 kg, and there's the stiffness 15 kilonewton per meter, and damping coefficient is 15% of the critical. So I can say that one has C is equals to 0.1 times 15 times of Cc. So I have to find out critical damping factor, natural frequency of a damped coefficient, that is omega d. I have to find out logarithmic decrement delta and x1 by x2 value. So the first one, let us go for the critical damping coefficient, so which is given by Cc is equals to 2m omega n. So since we know the k value and m value, it is very easy to find out the critical damping of coefficient first. So I go for substituting the value. So omega n I'm going to take as root of k by m. So I'm going to substitute k value, m value over here. So I'm going to get that Cc is equals to 1224.7 Newton second per meter. So once you got Cc and C value they given in terms of Cc, it will be very easy to find out the damping factor eta, that is eta equals to C by Cc. So C I go to substitute as 0.15 times of Cc divided by Cc. So Cc will get cancels. I'm going to get damping factor as 0.15%. So damping factor is less than 1. So since it will be a underdamped system. Coming on to damped natural frequency, so that is omega t is given by omega n into root of 1 minus zeta square. So omega t I am going to substitute. So omega n nothing but root of k by m multiplied by root of 1 minus 0.15. I am going to get damped natural frequency as 24.22 radians per second. So coming to next, logarithmic decrements. So logarithmic decrement you can use many of the equations. So I want to use the equation since I know the zeta value. So delta is equals to 2 pi zeta divided by root of 1 minus zeta square. So zeta value is known, substitute the value. So I'm going to get logarithmic decrement as 0.9533. And they asked to find out the consecutive amplitude ratio of a underdamped system. So ratio will be equals to delta ln x1 by x2. So delta is already known, that is 0.9533. I'm going to substitute ln x1 value, x2 value I have to find out. So I'm going to take that. That will be e to the power of 0.953. So I'm going to get x1 by x2 is equals to 2.594. That is with the ratio of consecutive amplitudes of a underdamped vibrating system. So let us consider the next problem. A mass of 4.5 kg hangs from a spring and makes damped vibration. The time of 50 complete oscillation is found to be 20 seconds, and the ratio of first downward displacement to the sixth is found to be 2.25. Find the stiffness of the spring and the damping force. So from the equation, the given data will be mass is 4.5. The ratio between x1 to x6 is 2.25. And they given the time, that is time taken, that is number of time taken divided number of seconds, that is 20, and divided by 50 oscillations, that is going to get as 0.4 seconds. And you have to find out k value, that is stiffness, and the damping force F. So from the thing, so delta they given 1 by n ln x1 by x2. Sorry, x1 by x6 they given. So I'm going to substitute. So since it has to go for 5 complete cycles, I'm going to take as 5. So 1 by 5 ln 2.25. I'm going to get logarithmic decrement as 0.162. So once you got the logarithmic decrement, it will be very easy to find out zeta value. So damping factor equation, I'm going to go for delta is equals to 2 pi zeta divided by root of 1 minus zeta square. For a zeta small, delta will be equals to 2 pi zeta. So zeta will be equals to delta by 2 pi. So I'm going to get that one as zeta as 0.025. Since it is less than 1, it is an underdamped system. So omega t is equals to 2 pi divided by td. So td is nothing but 0.4, which you already calculated. So omega t I'm going to get as 15.71 radians per seconds. So omega t is equals to omega n root of 1 minus zeta square. So omega t value I'm going to substitute over here. So omega n I'm going to get as 15.715 radians per second. So once I know omega n, I easily identify the k value because m value is known. So I go for k is equals to omega n square multiplied by m. So I'm going to substitute, I'm going to get that one as 1111.33 Newton per meter. So once you got the k value, I have to find out the critical damping. For a critical damping, I want to use the formula Cc is equals to 2m omega n. So one value I want to substitute as 4.5, omega n you already calculated, that is 15.715. When I go to substitute, I want to get critical damping as 141.435 Newton second per meter. So zeta damping factor is equals to C by Cc. So I have to find out damping coefficient. C is equals to zeta into Cc 0.2025 into 141.43. I got to get as 3.65 Newton second per meter. So once you got this value, I can easily find out damping force Fd is equals to C into x dot. X dot is nothing but the velocity they given as 1 meter per second. So I'm going to get the force of damping as 3.65 Newton. So coming to the next problem, determine the suitable expression for the equation of motion of a damped vibrating system shown in figure. Find the critical damping coefficient when A is equals to 0.1, B is equals to 0.013, K is equals to 4900 Newton per meter, and M is equals to 1.5 kg. So this is the equation given. So when I want to pull the mass, I want to give a mass, both the spring damper will be going for the resisting force, so that I have to calculate. So the distance is given as A and B. So let us assume the mass m is displaced at an angle of theta. So I'm going to assume it has been displaced either this side or this side as theta. So once it is displaced, the spring force I want to get is the spring force, that is K. It will be of B theta, that is K B theta, whereas damping it will be having a distance of A, so it will be C A theta dot. So I want to get inertia force, that is m a square. So a square is nothing but theta double dot. So I is equals to I naught theta double dot will be equals to summation of this. So I want to get as I naught is nothing but m a square into theta double dot will be equals to minus kb theta and the distance b I want to consider. So it becomes kb square into theta and c a theta into a, the distance. It becomes c a square into theta dot. So I want to substitute simplify the equation. So I want to get ma square theta double dot plus kb square theta plus a square into theta dot will be equals to 0. So when I want to take a and b, simply divide that one divided by b square, I am going to get as m double dot plus c dot plus kb square theta divided by a square equals to 0. Theta double dot plus c by m theta dot plus kb square theta divided by ma square equals to 0. So this is very similar to ax square plus bx plus c. So I want to get the solution like this. So solution will be minus c by 2m plus or minus root of c by 2m square minus kb square by ma square. So for a critical damping, the inside part should be equals to 0. So I'm going to take that. So I'm going to simplify that. I'm going to get as c square is equals to 4kmb square divided by a square. So I'm going to get cc square is equals to, substituting the values, I'm going to get critical damping coefficient as 222.90 Newton second per meter. So that is the end of the problems for a free damped vibration.